Okay, it's time to start. I got an email from somebody telling me that the median score for all the calculus classes was a 77. Ours was an 81. Isn't that fantastic? Yeah, okay, that's good. Very good, everybody. That's really good work. And 118 people in this class. We have about 220, but 118 got a B- or higher. You were in the B range or the A range. That's fantastic. That's outstanding. But now we have a problem. And here's the problem. You do well on the first exam. I've had this happen to me. I do well on the first exam. I'm like, this was easy. We'll be fine. I did well on the first exam. How bad could the second exam be? It could be pretty bad. It could be pretty horrible. All right, so we don't want to be doing that. So you guys are doing well. Let's just keep up the good work. I'm really happy with all of you. All right, any questions before I begin? Oh, I just ruined my beautiful thing here. No. Okay. Any questions before? When's the next quiz? Next Thursday. Look, I have my calendar on my notebook. When's the next exam? It's the 5th of March. The 5th of March. That's the next exam. Same time. I don't know if it's going to be in the same place or not. I'll send out all kinds of emails. They'll be posted on Carmen and so on. All right. So last time we learned the derivative of sine of x equals cosine of x, and the derivative of cosine is negative sine of x. All right, so I have a picture I want to draw for you that's going to maybe make this statement, I don't know, it's related. Today we're starting 3.5, and here's how the class is going to go. I'm going to draw this picture, and then we're going to go right into 3.5. I'm going to say like 2 sentences, and then we're going to work problems for the rest of the period until either I pass out or we run out of problems. If we run out of problems, I'm just going to say that's enough. I have a finite number. That's not that many, but we'll see. Okay, so here's this picture I have for the derivative of sine of x equals cosine of x. You start with a unit circle. And if you draw a unit circle, that's just a quarter of a unit circle, where is sine? What is sine on the unit circle? It's the y value. So if I have theta here, here's theta. Here, let me make this. Remember, sine looks like this, right? This is sine. This is sine of theta, and then cosine of theta. Cosine theta is down here. So let's go ahead and label that too. And if I recall correctly, cosine is blue. Cosine of theta. Now, when we take the derivative, what we're doing is we're changing the input by a little bit, and we're seeing how much the output changes. That's what we're doing when we take the derivative. So if we're going to change theta a little bit, right, then let's do it. Let's change theta a little bit. And here I'll put this in a different color too. So we're going to change theta by a little bit that I'll call, that's supposed to be an h. There, theta is changed by h. So this is theta plus h. And then here's where I'm going to do some weird stuff. I'm sorry, but this is actually a pretty nice picture if I can do it right. What I'm going to do, yes, think Bart, think, is I'm going to make a right angle right here, a right angle. So this is a a right angle right there. And do you believe me that if I leave this at a right angle that, and I go all the way up there, I claim that this distance, do you guys know what this distance is right here on the arc? Do you know what that is? You don't seem to know, which is okay, which is good because then I can tell you. It's just h. These are radians. The cool thing about radians is this arc length here is the angle. That's how a radian works. So if you have a unit circle, what's 90 degrees for a unit circle? Pi over 4, right? This length is pi over 4. Radians are very natural. If you aren't used to working with radians, now is the time to change. I cannot be emphatic enough about this. You must work in radians from now on because as we'll see on Monday, your answers will change in complicated ways if you start using degrees at the wrong time. We don't want that to happen. We want our math to be as easy as possible. It's already hard enough, right? Nobody's saying anything. It's okay. Yeah?
You said 90 was pi over 4 and pi over 2.
90 is pi over 2. That's right. God. Ugh. Yeah, I'm sorry. Okay, so 90, let's write the right thing down. 90 degrees is equal to pi over 2 radians. And so this distance here is pi over 2. Check? All right, awesome. So now, this distance here, if this is an angle of h, right, then this arc length is h. And so here's where I do a little bit of, I don't know, magic or something. I'm going to say this length is also about h. This is about h right here, this length here. And then what I'm going to do is I'm going to make a triangle. I'm going to make another triangle, and it's going to be a right triangle. And I'm going to, there we go. Is that what I want to do? Yes, absolutely. Can somebody tell me, I know my picture isn't the best picture. It's pretty good, come on. Here we go. So I have two triangles. You see these two triangles? And this is a straight line. What's the angle measure of a straight line? 180 degrees, right? Or pi radians. After I tell you I only want you to work in radians, I ask you a question about degrees. All right, and what's this angle here? 90. What's the sum of the interior angles of a triangle? 180. So if this is theta, and this is 90, then we have some other angle here, right? What's this angle have to be? What's this angle have to be right here? It has to be theta. This angle here is theta. This is a right angle, so these two angles are the same. These are similar triangles, so they're just scale factors of each other. So this side, how long is the hypotenuse here of this right triangle? 1. How long is the hypotenuse of this right triangle? It's h. So this side is h sine theta, and the blue side is going to be h cosine theta. So as I look, and this is the amount that I'm adding to sine theta as we increase the angle a little bit. So if I said, what's the change in theta? So delta theta, well wait, that's not right. Delta y over delta theta. What's the difference in sine as I increase theta a little bit? How much does it go up? it goes up h cosine theta. All over. Remember, sine theta just moves in this direction. Right? Over, what was the little change that we made? H, that's equal to cosine theta. This is just some sort of pictorial thing. It's about rates of change. And it's why I'm doing it to connect to the last lecture and also to connect to this. I'm gluing two disparate, I don't know what that word is, two different lectures together. All right. What questions do you have about this? This is really springy. Okay. No questions? We'll try not to break anything today. So, we have two ideas. Average rate of change, and we have instantaneous rate of change. Instantaneous. Is it OUS? Average rate of change versus instantaneous rate of change. So if I have P of x, and this P of t, sorry, and this is a position, the average, your average velocity, you guys can figure this out. You do this when you go on a trip, surely. You take the total distance and you divide it by the total time, right? And so this is going to be P of t2 minus P of t1 divided by t2 minus t1. Oh, what's this formula look like, by the way? Slope. It is slope. That's exactly what you're doing. Do you guys remember when you learned distance equals rate times time? I think I learned it in 6th grade. There we go, right? Slope. We're doing the same thing. We're just keep on. We never stop. All right. This is average. This is average rate. On the other hand, instantaneous rate, we compute that by looking at the derivative. And I'm going to write it this way. I'm sorry. The P prime is great. It's just fantastic. If you write that down, that's fantastic. I wrote it as dp dt. Why? Well, I thought the prime was going to be too hard for people to see to start with. But then after I wrote it, I realized, look, see this fraction here? This is supposed to be reminiscent of this fraction here. This is, I mean, that's why they chose the notation. So this is instantaneous rate. Instant rate. So all the problems that we're going to try to do here are questions related to these two ideas. And I want to do, so I'm going to start working on page 179. And I'm going to email your TAs so they don't repeat unless you ask them to. Unless, of course, I forget. But I sent myself an email so I wouldn't forget. Right? I'm doing that all the time anymore. So we're on page 179 to 181. And we're going to start with 37. Number 37. Why not start with 1, Bart? I don't know. I didn't want to start with 1 for some reason. Who knows? 37 looked like a good problem to me. Let's see what I think now. Population growth of the United States. Interesting? Okay, so we have P of t. So, do you guys know what I'm doing? What I'm gonna do is I'm gonna kind of read the problem. I'm not gonna write it all down, and then I'm just gonna try to solve it. If you guys get confused, hopefully all the technical aspects of this video work, and I can put it up and you can watch it again if you want to. Okay, so P of t equals population of US. Ooh, gotta put an S there. A, there we go. Population of USA in millions. You know, we could make this problem a lot more exciting. We should be like population of the United States of America in millions after zombie attack, you know, and then we could have like a okay, anyways, yeah. After 1990. Yeah, so that might be a best-selling book, you know, Calculus and Zombies. And every problem could be a zombie problem. There we go. So here's a picture of the plot. Is this right? Oh, okay. P prime is shown here. So I got to draw P prime for you. That's okay. I'm good at doing this stuff. P prime of t. 1, 2, 3, 20, 40. Wait a second. 60, 80, 100. What's that tell you about this plot? It's as fictitious as my zombie plot, because we haven't had 100 years after 1990 yet. They're very optimistic about the publishing schedule of this textbook. Okay, so now that's close. Okay, so that's their picture there. Okay, approximately A. Question A. Approximately when was the U.S. population growing most slowly? Oh crap. Bart just can't read. Damn it. 1900 to 1990. Okay, there we go. Approximately when was, oh, look at this. This makes perfect sense. When was the U.S. population growing most slowly between 1900 to 1990? So what's the answer to this question? The population was growing most slowly, he says, like in the 1930s here. Of course, yeah, it's even that way in the real one too. Yeah, 1930s in our picture and on the real one. B, it was growing the slowest in the 30s. Approximately was the U.S. population growing most rapidly? Like, it's supposed to be like between, it's growing, oh, this is the population growth, yeah, the 60s, okay? And they want us to estimate the growth rate in that year. And so it's about, what's the growth rate about in this year? Here. There we go. What's the growth rate about? 3, and what's that mean? 3 million per year. 3 million per year. And what about this one, the 30s? It looks like it's about 1 million, right? 1 million per year. By the way, if you look at the chart in the book and you decide that I'm wrong, that's okay, because we're looking at the chart here, because that's the one that everybody can see. Make sense? All right. C, what year, if any, was the population decreasing? Was the population ever decreasing here? What's this a plot of? The derivative. And the derivative is positive, so the population was always increasing, right? So C, population always increasing. Because the derivative was positive the entire time. All right. In what years was the population growth rate increasing? In what years was the population growth rate increasing? From here to here, it was increasing, right? From here to here, it was increasing. And from here to here, it was increasing. Are these hard problems? No, I don't think so. Now, if you haven't seen them before, it might be kind of tricky, right? Maybe. But so our goal is to make sure you've seen as many problems as we can show you, and then when you take the test, hopefully you'll be okay. Are there any questions on this one? Let's do another one. Let's see. Let's see what the next one is. Oh, let's do this one. This one looks great. Okay, so yeah. This is number 38. We're just going to plow right through this. Number 38. Here the story is, it's an economics problem. And so we have a production function. And so we're building something. Who knows what we're building? P of L equals 200 L plus 10 L squared minus L cubed. Okay, great. What are we building? Okay, production function gives the output. Ooh. Okay, so this gives the amount of production of widgets, I guess. Production of something per number of workers. So if you have more workers, you get more production done, usually, right? Although maybe you have too many workers, then they all play ping pong the entire time or something like this, and you don't get any work done. Maybe. I don't know. 3 supervisors for every worker, right? We could have we got P, okay, whatever. Okay, so now, yeah. Okay, so we have the average product. Okay, so the AP, AL, equals the average output per worker. Okay, great. Okay. And, right. And so, look, A of L is equal to P of L over L. You find out your production that you have with 18 workers, and you divide it by 18. Does this make sense? This should make you should be like, yes. Yes, that makes sense to me, I hope. If it doesn't, just ask a question. I'll just try to explain it better. That's all I'll try to do. All right? Okay, so this is average output. Great, 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 great. And then the marginal product. The marginal product this is M of, should be M of L, or yep, M of L equals dP dL. It's the derivative. And it basically says if you add one worker, what's going to happen to your production? You're going to add one worker, see what happens. Okay, great. For the production function given here, graph P, A, and M. I'm not going to do that for you if that's okay with everybody, but let's compute M, right? So can somebody tell me what M is equal to? Can you tell me what M is equal to? If not, that's okay. He says no. We're just taking the derivative of this function with respect to L. Can you do it now? Okay, tell me now. 200 plus 20L minus 3L squared. Okay, fantastic. Fantastic. Can you tell me, what's going to happen to the production as we add laborers. It's going to increase, but what's that minus L cubed doing out there? Oh, it's maybe cost. It's supposed to be production, you know. So I'm imagining it. Yeah, I'm imagining that you're filling the room actually. That's just my imagination. Nobody can get any work done. That's my theory. But it could be cost, okay? It's production though. Anyhow, okay. Suppose peak average product curve. Oh God, occurs at L equals L naught. Okay, great. Wow, I'm not sure if I know how to do this problem. Let's try to do it, okay? So peak average production. So what you want to do is you go through and you add workers. You add workers and you try to figure out how many workers gives you the best average production. Does that make sense? And so you put more workers in and then you compute PL. What's PL divided by L, by the way? We can compute this, can't we? Yeah, it's 200, oh that's not, so you take this. This is P of L, right? 200 plus 10 plus 10L. Oh, I know how to do the problem now. See, look, literally, I did not know how to do the problem, and I was scared because everybody's staring at me, you know? But now I know how to do the problem. What changed? What did I do? What did I do? I kept on doing steps, and I just kept on reading the problem, doing steps, until something happened that was going to help me. Okay, so minus L squared. So this is, and what we're supposed, and so peak average is the maximum, and they say it's when, they say it's when A prime of L, oh my God, A prime of L is equal to 0. So, and then so we want to find when A prime of L, I'm reading the problem, that's where I'm getting all this from. We want to know when A prime of L equals 0. So can you guys compute A prime of L for me? This is equal to 10 minus 2L. Is that correct? Okay, so what value of L, boy, I hope this works. I have no idea. I really don't know what's going to happen here. That's what makes it exciting. Can you solve for L here? So what they want you to say is, hey, if it's the case, this is the question. They say, prove. Yikes. Prove. The question in the textbook is this. So now you have all the information. They say this. They say, prove if A prime of L naught equals 0, M of L naught is equal to A of L naught. Makes sense? What's it saying? So let's say it in words. So they say the rate of change of your average production, so if that equals 0, then M of that value equals A of that value. Let's see it happen for this specific case. Let's see what happens. Is that okay? Does anybody know what's going on? No? Okay, where do I start? She shook her head no, so come on, help me out here. Because I know that I know there are other people, and if you could just back me up a little bit, I'll do a better job, I promise. Where should I go? You don't know. Okay, I'll start from the very beginning. So now, we have a production per number of workers here. This is the average output per worker. And it's equal to this divided by the number of workers. That makes sense, doesn't it? I'm looking around. If you lie to me, you're only cheating yourself. Marginal production is you just take the derivative. Okay, and we did that. Oh, and by the way, we computed this, and hopefully we didn't make any mistakes, and hopefully we didn't make any mistakes with the derivative. And now the textbook tells me, it says to me, but if L prime, sorry, if A prime of L equals 0, then this happens. And so I'm like, really? That happens? Is it okay? Is it, you know what's going on? Or? You know what we need to do? What were you going to say? Hey.
Well, I don't know. It's on, we take the derivative of A of L, why do that?
When we take the derivative of A of L, y what?
Like why?
Why did I do this? Oh. I did it because they say, hey, prove if A of L naught equals 0. I was reading this part right here. That's why I did that. I'm sorry. It's my bad. Yes?
Question. What does marginal product mean? And how do we know to take the derivative of L to make marginal product?
Okay, they tell you that. They define marginal product as the derivative of the production.
Okay. And is A prime of L 0 because there's no production rate and there's no labors?
Is A prime of L 0? No, we're finding the specific value. When is, and so when the derivative equals 0, that's usually when you're at a maximum. It's when your growth is something at a maximum or a minimum. Yes?
How did you get 10 minus 12?
Yeah, good question. Let me think about this real quick. I know what A of L is right here. And we took so the derivative of 200 is 0. The derivative of 10L is 10. And the derivative of L squared minus L squared is minus 2L. Yeah, back there.
For that answer of A, which is PL over L, how did you put the P, you put PL over top of L, what did you use for the bottom of the denominator?
L. So I literally went through here. I factored out an L and divided it out. And then divided it out. Is it okay? All right, so now, what the heck do I do? It's okay, let's find out. So we have 10 minus 2L naught equals 0. Let's solve for L naught. Minus 2L naught equals negative 10. L naught equals 5. Plug 5 into M of L naught and A of L naught. All right, so now we're going to have, M's over here. Yikes. Okay, so M of 5 is equal to 200 plus 20 times 5 minus 3 times 5 squared. Okay, and this is, 20 times 5. 20 times 5 is 100, I know that. That's 300 minus 75. That's 225. Is that right, everybody? Okay, and now I'm hoping that this is equal to, I'll put question marks here because that's what we're trying to explain. A of 5. That's 200 plus 10 times 5 minus 5 squared. Oh, it works! Okay, so 200 minus 10 times 5, or plus 10 times 5 minus 5 squared, which is equal to, okay, so I've got good news for everybody. So that looks good, right? Then we've answered the question. I've got good news for everybody, and I've got bad news for everybody. Which one do you want to hear first? The bad news is there's more to the question. We're not done with it yet. We might be done with it, but it's not done with us. The good news is we got that part right. All right, so I read the question a little bit closer, And I realized it said, show that for a general production function, this is true. So why should this be true completely in general? You understand what I'm saying? If we don't know anything about, we use specifics about this function. We used its formula. Can we explain why this should be true even if we don't know anything about the formula? I think we can. Let's try. Let's just try it out. Check this out. Can you tell me, okay, so what is A of L equal to? A of L is equal to P of L over L. And here I have A of L prime, right? Can you take the derivative of this for me? What rule do we use? We use the quotient rule. So A prime of L is equal to something over L squared. Now it's low d high, so L P prime of L. Oh, this is going to work out beautifully. I'm feeling it. I'm feeling good. Okay? L P. Oh, this is easy. Sorry, we got it. We're going to win. Okay, so now minus, okay, this is, right? Minus, high d low. P of L. And what's the derivative of the denominator? 1. All right, so here's this. Now, what do you know about when you plug L naught into this thing? What do you get out? 0. So 0 is equal to L naught P prime of L naught minus P of L naught. Ugh. Okay, no problems. Just relax, Bart. Everything's going to be cool. Just relax. Stay cool, Bart. Now, what's going to happen? Oh, I need to explain why M. What's M? Oh, M's equal to P prime of L, isn't it? Isn't it? Aha. So look, so this is equal to, I can start saying, well, this is equal to L naught M of L naught minus P of L naught over L naught squared, right? What do we do now? Does anybody know? Write it as two fractions. L naught over M of L naught all over L naught squared minus P of L naught over L naught squared. And this is equal to 0. Multiply both sides by L naught. Multiply everything by L naught squared. Multiply everything by L naught squared. Nice. Didn't need to do that, I guess. And now divide everything by L naught. Can you divide everything by L naught? I say we're done. Because what is A? A is P of L over L. So 0 equals M. This is a hard question. This is harder than I thought it was going to be. So this is M. I hear you. I got you. L naught. And so this is equal to 0, which is equal to M of L naught minus A of L naught, which is exactly what we wanted to explain. Boy, that's a hard step. I hope you don't see something like this on your exam, because this is something that I think would be really, it's kind of abstract, right? But it's possible. Your next exam. If you didn't understand, yes. I see it. Do you understand up to this point? Maybe? M is P prime. It's how the economists do it. Marginal means take the derivative. I'll get you in a second. How to get ML not here? What's this thing equal to? It's equal to 0. I just multiplied everything by L naught squared. If I have A plus B over 3 equals 0, can you say, hey, that says that A plus B equals 0? You just multiply both sides by 3. Where did that, yeah. You still have another question? Okay. All these things are equal to 0. So I just multiply both equations by L naught, both sides. No. That's not a good answer. You don't believe me. I don't like that. No, okay, well, you don't see it. Oh, I'm sorry. Sorry. He says, what about this L naught, Bart? I know how you got rid of this one, but what about this one? I divided everything by L naught again. So multiply everything by L naught, you get rid of this one. Divide everything by L naught, it puts it down there. All right, can we move on from this horrible problem? All right. You should go over this again. Okay, velocity of a marble. Now we're moving from advanced economics to elementary school games. Here we go. Velocity of a marble. So the position of a marble rolling up a long incline, that's impossible. Okay, so rolling up a long incline. Oh no. Oh well. So the velocity of a marble rolling up a long incline is given by the position, which of course is denoted by S equals 100t over t plus 1. T is in seconds. So what's S represent? Position. Okay, and S equals 0 is the starting point. Okay, great. Fantastic. Graph the position function. Do it yourself. Okay. Find the velocity function for the marble. What's the velocity function for the marble? What do? I compute the first derivative. I compute S prime. I compute the derivative of S with respect to t. So oh, you guys probably can't see that well enough. So S prime is equal to, oh my God, what do I have to do here? Quotient rule. Okay, so t plus 1 squared over, under t plus 1 times 100 minus high 100t, the low, which is 1. Look good? This is the velocity. That's the velocity. Okay, great. Graph the velocity. We're not going to do that. Oh, at what time is the marble 80 meters from its starting point? This is meters, by the way. This is S is in meters. So when is it? So what do we have to do? We want to know when it's 80 meters from its starting point? What? Set S equal to 80. So we say 100 t over t plus 1 is equal to 80. Solve for t. Solve for t. Let's do it. Time to solve for t. 100t is equal to 80 times t plus 1, which is equal to 80t plus 80. What do I do now? I could divide by 100, but I could also subtract 80t from both sides, which is going to make my life easier. Subtract 80t from both sides, I get 20t is equal to 80. Now I divide by 20. Divide by 20. T is equal to 80 divided by 20 is 4. Is that right? Awesome. So after 4 seconds, we're 80 meters up the ramp. Wow. Now the next question is probably going to be, how fast are you going? Oh no, at what time is the velocity 50 meters per second? How do we solve this problem? Set this equal to 50, solve for t. Is that hard to do? Okay, we're not going to do it then. You guys should go ahead and do that one. Ooh, I like this next one. What questions do you guys have about this? Do you prefer y'all? No comment. Okay. So let's do the next problem. So this was number 39. We did 37, 38, 39. Now we're going to do problem 40. Problem 40. Problem 40. It's tree growth. Okay, so what's a conifer? Does anybody know what a conifer is? What's a pine tree? No, that's an evergreen, right? Okay, so let B represent the base of a conifer tree and H represent the height of the tree. Okay, so here we have some sort of, there's our conifer tree. Looking good, right? Huh? And let's see. There we go. And so now there's B, and the height of the tree is H, which will be in purple. Good? Okay, awesome. Assume the height is related to the base diameter by this crazy function I'm about to write down. So the height is related to the base of the diameter. Wait, the diameter of the base, probably. Measured by the base diameter. Wow. Okay, so here we go. H is equal to, 5.67 plus 0.7b plus 0.0067 b squared. Okay, it says graph the height function. Are we going to graph the height function right now? No, forget that. But what's it look like, by the way? It looks like a parabola. It opens up, and you see how this is a small term in front of the b squared? So it's going to look fairly linear and then kind of spike up later on. Does that make sense? It's going to be pretty flat, I think. I'm often wrong. I think I'm right though. Anyways, plot and interpret the meaning of dHdB. dHdB. What the heck is dHdB? The derivative. So what is the derivative? What does it mean? Changing the height as what changes? As the base grows a little bit, this is how much the height can change. Make sense? Those ideas repeated over and over and over again are what this section 3.5 is all about. Have a nice weekend, everybody.